Okay, think we're going. Alright, so let's do a quick recap of what we talked about last week. What did we talk about last week?
Set or functions.
No, we didn't talk about functions. Huh?
Order pairs.
Order pairs, we talked about
Relations.
order, there we go, relations. We talked about relations. What was a relation?
It's a specific ordered pair.
A set of ordered pairs. Now, technically there were different types of relations, right? I could have a tertiary relation, which is sets of ordered triples. I could have a four-nary relation, which is sets of four-element lists. But we said from here on out, we're only going to care about binary relations, so sets of ordered pairs. So from here on out, anytime we say relation, we mean a set of ordered pairs. We don't care about the other ones, right? And we were talking about some of the properties that those relations could have. They could be reflexive, they could be distributive, no, symmetric. What did it mean for a relation to be symmetric?
Irreflexive.
It means, doesn't mean x is equal to y, but y is equal to x.
Nope, it means if x is related to y, where r is some relation, that implies y is related to x.
Yeah.
Right? So sibling is a reflexive, or is a symmetric relation. If I'm your sibling, you're my sibling. We also had, what's another one?
Asymmetric.
Asymmetric. What does that one mean?
X not related to y, y not implies y is not related to x.
If x is related to y, then y is not related to x.
Oh yeah.
Right? What would be an example of that? The mother relationship. If someone's my mother, it's guaranteed that I am not their mother. Right? For a few reasons. Next one. What's another one?
Wasn't there one that was reflective?
So we had reflexive. Do we remember what reflexive was?
Isn't it x
X
is related
related
to
to x.
y and y is related to z, so z is...
No, that's transitive.
That's x
So we'll come back to transitive. X is related to x. X is always related to itself. What's an example of a reflexive relation? Huh?
No, that's
Equals. X is always equal to x. There's a good reflexive one. Is the same height as. Jacob is always the same height as Jacob. That is a reflexive relationship. Then the counterpart to reflexive was irreflexive. What did irreflexive mean?
they're not equal.
X is never related to itself. Reflexive meant x is always related to itself. Irreflexive meant x is never related to itself.
So I found mother or whatever.
Right, so mother would be an irreflexive relationship. We're guaranteed that no one is their own mother. That's never the case. Okay, so that's just some refresher on what we did last week. We're not going to be dealing with those relationships from here on out, but they come up over and over again in every single field of math. In particular, reflexive, transitive, and symmetric. If a relation had those three, then we called it a equivalence relation.
Yeah.
And basically, every field of math is very interested in particular equivalence relations. The equivalence relation you're very interested in geometry is congruent. In fact, that's what the axiom says. If you go look at your geometry axioms, if you're using Hilbert's axioms, one of the axioms, it doesn't use that terminology because they don't expect you to know what those words mean, but they'll say congruence. Everything is congruent to itself. If A is congruent to B, then B is congruent to A. And if A is congruent to B and B is congruent to C, then A is congruent to C. They're basically saying congruence is an equivalence relation. That's what the axioms are saying. So every field of math, equivalence relations come up all the time. Equivalence classes come up all the time. You remember what an equivalence class was?
When everything inside of it. Isn't
Once you have an equivalence relation, so if I have a set and an equivalence relation, I can then put every member in the set in one and only one equivalence class, which is all the things that are related to those same things. So for example, in a classroom, the equivalence relation I could use is has the same last name. And I can divide everyone up by their last name. every person in the class will be in one and only one of those groups. Right? I could also break everyone up by same height. Right? That would be an equivalence relation. You can imagine I take the whole world, I take everyone who's 6 feet tall, put them here, 6'1" over here, 6'2" over here, break it all up like that. I could then take every person on planet Earth and put them in one and only one of those equivalence classes. That's how I know that same height is an equivalence relation. Equivalence relations can always produce equivalence classes, or if I have an equivalence class, I could reverse engineer that into an equivalence relation. Same thing. Another word for those equivalence classes, a more intuitive word, is a partition. Partition on that. But, so we'll definitely do a lot more of that in discrete math. So you guys will get more, but it comes up again and again in every single field of math that we do. And even when we're doing set theory, if we decide to continue on development of set theory further than I'm thinking, if we wanted to like develop the plus relationship, if we wanted to build the integers from the naturals, if we wanted to build the rationals from the integers, we'd have to use equivalence classes to do that. Because, for example, 1/3 and 2/6, when we're building the rationals, are in the same equivalence class. We're saying 1/3 and 2/6 are somehow the same.
Right.
So, let's get to functions. Functions. So, a function is a special type of relation. A relation is just a set of ordered pairs. A function is a special type of relation. It satisfies a property. A relation f is called a function provided that anytime I have AB inside the relation and AC inside the relation, I'm guaranteed B equals C. Now, what's the high-level way of viewing this, or the intuitive way of viewing this? We're saying that every left-hand element goes to the same right-hand element. So if A goes to B and A goes to C, B and C better be the same thing. So let's look at these two and see which of these is a function and which of these isn't. So F and G are both relations, right? They're just sets of ordered pairs.
Okay.
Is F a function?
No.
Why not?
Square.
Square goes to triangle.
Yeah, we have square goes to 3 and square goes to triangle. But 3 is not equal to triangle. Right?
Mm-hmm.
Is G a function?
Mm-hmm.
Yeah.
Yes.
It is?
Mm-hmm.
But I never have two things in there like this, do I?
No.
Mm-hmm.
So how is it a function?
Because you never have it.
We do have two things in there. Look, take 2, 4 for this one, and take 2, 4 for this one.
Mm-hmm.
You can pick the same thing twice. There's no requirement that B and C can't be the same thing, because they better be the same thing. So don't get confused by the fact that we have a B and a C here, so you think you got to get two different things in there, because no, what we're saying is they better be the same thing. That's what we're saying.
Well, you can get 2 square 3s.
2 paired to something's only in there once. If it's in there twice, then it doesn't really matter. You can say it's only in there once because you can't have duplicates in a set. Right?
Yeah, you can.
Huh?
You can have duplicates in the set.
But it doesn't change the set. In other words, I did not write a different G. G is still exactly what it was. Right? Okay, so that's a function. Every left-hand element is paired with a unique right-hand element. I can't have one paired with 2 and one paired with 3. I can only have one paired with one thing. Feel like we got a good feel for what a function is? Special type of relation
Well, we
satisfies this property.
In every geometry class.
Yeah, relations of functions come up. Doesn't matter what math class we're talking about, they're going to come up. Now, when we're dealing with a function, we have a special type of notation that you're no doubt very familiar with, but let's go over it anyways. So let f be a function and let x be an object. Then f of x, you're used to seeing that, is defined if and only if there is a y such that xy is an f. In which case, we say f of x equals y. This is shorthand for giving me the thing paired with x. F of x is the element paired with x. Y. So if xy is in f, if that tuple's in there, that ordered pair's in there, then what is f of x? The thing it was paired with. That's what we mean by that notation. So let's do some examples real quick. Looking at f from this example, what's f of 1 equal to?
2.
2. What's f of 2 equal to?
3.
3. What's f of 4 equal to?
5.
5. What's f of squared equal to?
Trick question. Undefined.
It breaks down, right? That's why we said let f be a function. Here it wasn't a function, so the notation isn't defined in this case. Make sense?
Yeah.
And here's why it's not defined. When we tried to do that, broken. Doesn't work. On the other hand, the g we know is a function, so we better not break down doing that. So what's g of 1? 3. What's g of 2?
4.
What's g of 3? What's g of 4?
6.
Wonderful. Okay. Special notation. So we're very interested in, no doubt you've all seen this function before, f of x equals x squared.
Yeah.
Right? You've all seen that function before. Now let's pretend that we're just talking about integers only. So we're only plugging in integers for x and we're only getting integers out for y. You good with me so far?
Yeah.
Okay. So you've seen this notation a lot. This notation is used to represent an infinite function. A function that's a set of an infinite number of ordered pairs. And this is just giving you the relationship. They're saying whatever the left-hand element is, to get the right-hand element, just square the left-hand element. You want to know the thing paired with 3, it's 3 squared, or 9. So this is a shorthand way for writing out this infinite set. Negative 2's paired with 4, negative 1's paired with 1, 0's paired with 0, 1's paired with 1, 2's paired with 4, etc. So that's what we mean by this shorthand notation. When I say let f of x squared be a function, I'm saying this is shorthand for this infinite set, so that we don't have to write it out. In case there's any ambiguity, here's the exact set we're talking about. Where we're saying f is, it's a set of all ordered pairs x, y, where x and y are integers, and y is equal to x squared. That's what this set is, and that's what this set is. These are all talking about the same set, the same function. Is there anything weird in any of those ways of writing it? This is exactly what your textbook meant every time it showed you that, in all your algebra classes. Anytime you saw f of x equals x squared, it was shorthand for this, except for they were saying for all real numbers, not just integers. We just did integers here. Good? Okay. So, let's see what I've got there. Oh, the domain, and then we said codomain in this book. So, going back to relations, remember what the domain of a relation was? All the left-hand elements. And the codomain was? So since f is just a function, or since a function is just a relation, it also has a domain. Make sense?
Yeah.
Now, we talk about the codomain of the relation when it's a function as its image. So we don't say the domain and the codomain, because codomain, we'll see what we mean by that gets changed down the road. So we're going to talk about the domain of f, or the domain of a function, is all its left-hand values. And the image of f, or you've also heard, what is it? What do you hear for all the lines? Range, thank you. Image of f, or the range of f, is all the right-hand elements. Good? So, let's do that real quick for, I don't know what I was thinking about doing that for. Because up there, it would be g. Let's do it for g. What's the domain of the function g up there? 1, 2, 3, 4. And its image is?
3,
4, 5, 6.
3, 4, 5, 6. Maybe let's look at this one real quick. So if we're looking at the image of f from this example, what's the image of f? Or sorry, start with the domain. What's the domain of f for this function?
X, all the integers.
All the integers. Remember, we're talking about this order, we're talking about this set. This is shorthand for this set. What are all the left-hand elements in there?
All the integers.
It's all the integers. What are all the right-hand elements in there?
All the integers, squares, x
The
squared.
natural numbers.
Not the natural numbers. Notice we're never going to get 2.
Perfect squares.
All the perfect squares.
And their negatives.
Nope.
Oh, right.
So 0, 1, 4, 9, 16, etc. Just perfect squares. Okay, so that's the domain, that's the image. Good with that?
Mm-hmm.
Yes, Pappy.
Huh?
Yes.
Okay. And then we also had a notion of a relation from a set to a set. So I said that the relation R was a relation from A to B, provided that R was a subset of A cross B. Maybe stop real quick and remind ourselves what A cross B was. What was A cross B?
It's the Cartesian product between B.
Yeah, but what does that give us?
Is that
Everything in A and everything in B.
It's not very precise.
it's a set
It's
of
their
ordered pairs
intersection.
where all the left-hand elements are elements of A and all right-hand elements are elements of B.
Perfect. A cross B is a set of all possible ordered pairs we can make where the left-hand element comes from A and the right-hand element comes from B.
Right.
Good?
So
So a relation R, we say it's from A to B, provided that it's a subset of this. Since this is a set of ordered pairs, R, if it's a subset of that, R is also going to be a subset of ordered pairs. All its left-hand elements are going to be in A, all its right-hand elements are going to be in B. Right? Or in other words, the domain of R is a subset of A, and the codomain of R was a subset of B. Another way to say that. You with me so far?
yeah,
Do we need to draw out a picture, or do you think you got it?
draw a picture. Is A set of ordered pairs or not?
It's just a set of anything.
That's
So we could do A is just a set, 1, 2.
right.
We could do B is just a set, 3, 4. And then I could say R is equal to 1, 4, 2, 3. R is a relation. Notice all its left-hand elements are in A, all its right-hand elements are in B. Therefore, it's a subset of A cross B. Think we got it?
Yeah.
Yeah.
Okay. And then, also, we said that R was a relation on A, provided that R was a subset of A cross A. Good? Just a reminder there. So, we're going to come up with a similar notion. A notion of creating a function from A to B. And it's going to do a similar thing. It's going to be a relation that maps all the elements in A to an element in B. So let me draw a picture first of how we're going to say this, and then we'll go over the definition. So now I've drawn A. A is a set 1, 2, 3, we'll say. B is a set 4, 5, 6. And F is going to be a function, some mapping. It's going to pair 1 to something, 2 to something, and 3 to something. So in this case, 1 goes to 4, 2 goes to 6, 3 goes to 6. You go with this picture instead of me writing out the set?
Yeah.
So, we're going to say that F is a function from A to B if it maps every element in A to an element in B. That's going to be the definition that we go over here. Feel like you have a high level understanding of it?
I thought we already defined function.
We defined a function. Now we're going to define a function from A to B. We're going to define this notation.
Okay.
All right?
It's similar to a relation from A to B, isn't it?
It's almost the same. If we had a relation from A to B, then all we required was that the domain was a subset of A. When we have a function from A to B, the domain is going to be all of A. It has to map everything in A to something in B. It doesn't have to use all of B, but it has to use all of A. So, let's go over it now. Let F be a function and let A and B be sets. We say that F is a function from A to B, provided that the domain of F is equal to A, and the image of F is a subset of B. It can be equal to B, but it has to at least be a subset. Notice, also, in all this, F is still, any F we draw here, F is also going to be a subset of A cross B, right?
Yeah.
All its left-hand elements are still going to be in A. All its right-hand elements are still going to be in B. So it's going to satisfy this. It's just a little bit more restrictive than this. So, let's go. Let f be a function, let a and b be sets. We say that f is a function from a to b, provided that the domain of f is all of a, and that the image of f is a subset of b, and we write f from a to b. That's the definition of what we mean by the symbol. When you see f from a to b, we're saying f is a function whose domain is a and whose image is a subset of b. Now, when we have a function, and we mark the set that it's from and the set that it's to in this way, then we typically call the function a map. It's not a new definition. Map and function, they're synonyms, they mean the exact same thing. It's just that when the function's like this, we might say the word map instead of the word function. And we typically say the word map instead of the word function to help you keep it track in your head. Oh yeah, this was a function from a set to a set. So I might accidentally say map. I'll try to only use the word function here, but just for future reference, they often use the word map. So let's look at some examples. So let f be a function from all the real numbers to all the real numbers by f of x equals the absolute value of x. Is there anyone here who doesn't know what the absolute value function does? Is that funny?
Yes.
You remember how much you struggled last year with absolute value proofs?
Still.
Still? Yeah. So, absolute value. What's the absolute value of negative 3?
3 to negative 3.
And what's the absolute value of 3?
Negative 3.
No, 3. Okay. So, notice, I shouldn't have written these out, I should have made you say it. What's the domain of that function?
It's still real numbers.
It's all real numbers, right? Duh. F is a function from R to R. What does that mean? It means F is a function whose domain is R and whose image is a subset of R. Right? What's the image of the absolute value function?
No, positive numbers.
All the non-negative real numbers, or all the positive real numbers, including 0. Have you seen this notation before?
No, never.
Throw something in there. This is a notation. It means we're taking all the numbers starting at and including 0, going off to infinity in the positive direction. But if you're not familiar with that notation, that's fine. Just understand that the answer is the image is all the non-negative real numbers. All the numbers greater than or equal to 0. Make sense?
Yeah.
So, all the numbers greater than or equal to 0 is a subset of all the real numbers. It works. Alright, let's look at another one. Cover that up, even though you probably already read it. So, we have g now is a function from the real numbers to the real numbers, given by g of x is equal to x squared plus 5. What's the domain of g?
All real numbers.
How do you know?
Because it's a function of real numbers.
By definition, g is a function from the real numbers. The fact that the real numbers is right there means its domain has to be the real numbers. Otherwise, I'm lying to you. And what's the image of this function?
All the
numbers.
5
All the real numbers.
5 to infinity.
5 to infinity. All the real numbers greater than or equal to 5.
Right.
Right? We can't get anything smaller than 5 from this.
Right.
There's no number I can plug in such that when I square it and add 5 to it, I get a number smaller than 5.
Okay.
All the real numbers.
Huh? Did you say pi? I? Is that a real number? Or is it an imaginary?
We can imagine. Got it.
I can't.
Oh, you do that.
Anytime I imagine I, it comes out complex.
Oh, you got me there.
Okay. Examples. Okay, so we have the sets A, B, C, and D. Right? And now the G here is this G. Let's get rid of that so that we don't get confused. Okay, question. Is G a function from A to B?
You got let's think about this.
I know. That's why I paused.
Yes.
Yes?
Yes.
You gotta wait for Jacob to catch up. Yes? Alright. Is it a function from C to D?
No.
Why?
Because of
7.
Because I-
It is.
Because of 5.
Oh, because of 5.
It doesn't map 5 to anything. C, if there's a C here, then the domain of G better be all of C. 5 is not in the domain of G. Therefore, it is not a function from C to D. Is it a function from A to D?
Yes.
There's no 7.
What's your point? So,
All right. Finally, is it a function from C to B?
no.
No. All right. So I think you're getting a feel of what it means for a function to be from a set to a set.
No.
Good. All right. Now remember what an inverse relation was. So G's a relation. What's G's inverse relation?
Solve
3, 1,
3, 1,
4, 2,
4, 2,
3,
5, 3, parenthesis first,
4, 8.
5, 3, comma, 6, 4. And that ends that. So that's our inverse relation. If this G is this relation, G inverse is this relation. So notice taking the inverse of a function just gives you
Reverse image.
a relation. Not necessarily a function. It could be a function, it might not be a function.
Right.
In this case, did it happen to be a function?
Yeah.
Yeah. When we took the inverse of G, we happen to get a function, but we're not guaranteed that that will happen.
Right.
We are guaranteed it will be a relation. So our inverse relation is the same thing as an inverse function. We're doing the same operation. When I take the inverse of a function, I'm not guaranteed I'll get a function. I might get a function, but the way you take the inverse of a relation is the same way you take the inverse of a function, since a function is just a relation. Right? So what do we say here? If f is a function, then f inverse is a relation, for sure.
Yeah.
F inverse might also be a function. In this case, G inverse was a function. Let's look at a case where it doesn't work. So here's f. We're going back to the square example. -2 goes to 4, -1 goes to 1, 0 goes to 0, 1 goes to 1, 2 goes to 4. Now let's look at the inverse. 4 goes to -2, 1 goes to -1, 0 goes to 0, 1 goes to 1, 4 goes to 2. What does 4 go to?
-2 and 2.
-2 and 2. So f inverse in this case is not a function. F was a function, f inverse not a function. G was a function, G inverse was also a function. So we're not guaranteed that the inverse still gives us a function. Before we move on, I wanted to point out another way that we could think about the definition of a function now that we have this function notation. So remember, the definition of a function was, if the left-hand element is the same, the right-hand element better be the same. Here's another way that we could write that. If x is equal to y, then f of x better equal f of y. If the left-hand values are the same, the right-hand values better be the same. Good? I'm just telling you this because this is personally the way that I like to think about it.
Well, but we've never seen the notation f of y.
Okay.
It,
Just f of x, okay, yeah.
yeah, x is a dummy variable.
Yeah.
I could have put, if I would have put a and b here, then this would have been f of a, f of b. I probably should have done that. Oops. Yeah, don't get confused by the fact that you're used to, it's such a terrible, not tradition, misconception that you come out of basic algebra with, the idea that f of x represents a function. Right?
Yes.
No, f of x is just, if f is a function, then f of x gives you the right-hand element associated with x. And you think that you can only have x's, and you're so tied to x's, and everything has to be an x, unless you're doing something's equal to x's, and that something has to be a y, because y's are what's equal to x's. And f of x is the same thing as y. All sorts of weird
Well,
stuff.
then you
like that.
start mapping f of y in algebra. All the time. It's called the inverse function.
Yeah, so the authors work so hard to follow a very simplistic, they be very consistent in how they use things, which causes your brain to make connections that are not valid connections. Because they're just trying to make sure you know how to solve the problem right. So that you get high scores on the test.
Right.
So that the school who bought their program's happy with it.
Right. world, everyone's happy.
Yeah, until you get to me in high school and I have to flunk y'all.
Right. So you're the problem.
Well, I'm a problem that's not going away, so better find a different way to solve me. Okay, so let's go on. So have this notation. So now we're going to look at a function f being 1 to 1. Intuitively, a function is 1 to 1 if every right-hand element is paired with one left-hand element.
Yes.
So a relation's a function if every left-hand element is paired with one right-hand element. And then a relation is, or a function is 1 to 1 if every right-hand element is paired with one left-hand element. So notice here, is G 1 to 1?
Yes.
G here is 1 to 1 because 3 only comes from one thing, 4 only comes from one thing, 5 only comes from one thing, 6 only comes from one thing. However, look at F here. Is this 1 to 1?
No.
No, because 4 comes from -2 and 4 comes from 2. So it's not 1 to 1. Another way to check is a function 1 to 1 is take its inverse. If its inverse is still a function, then it's a 1 to 1 function. So f is a 1, if f is a function, then f is a 1 to 1 function if and only if its inverse is also a function. Is another way that we could say it. But let's go over the exact definition and we'll talk more about it. So a function f is said to be 1 to 1 provided that anytime you have a BA in f and CA in f, or anytime you have ordered pairs with the same right-hand element, the left-hand elements are also the same. This is the way I like to think about it. F of x equal to f of y implies x is equal to y. If the right-hand elements are equal, their left-hand elements are equal. A function was, if their left-hand elements are equal, then their right-hand elements are equal. Good?
Yeah.
Okay. So, we talked about the inverse is also a function, then it's 1 to 1, right? So how do I know that f is not a function, or is not 1 to 1? Because its inverse isn't a function. How do I know that g is a 1 to 1 function? Because its inverse is also a function. If I had duplicate right-hand values, that's the same thing as its inverse not being a function. I don't know, trying to come up with a bunch of ways to say the same thing. Feel like you got it?
Yeah.
Okay. Then we'll move on to this. What? Oh, this was just something I drew along the way. Okay. So now let's look at the function f from the integers to the integers by f of x equals 3x plus 4. And let's prove that this is 1 to 1. How am I going to prove that it's 1 to 1?
Define maybe.
You're going to prove that f and that inverse.
Yeah, I can start with let f be let f from z to z be a function such that let f from z to z, z to z by f of x equal to 3x plus 4. So let whatever is given to me. Now how am I going to show it's 1 to 1?
Maybe start by dividing its domain. Oh, it's domain right there.
I need to show that anytime
You can show the domain and image are equal.
that doesn't do anything for me because think about this. 1, 2, 3, 4. Think about the function that maps 1 to 3, 2 to 4, and then the function that maps 1 to 4 and 2 to 3. Those are very different functions with the exact same domain and the exact same image.
That's the mistake we made last year all the time.
Are we already given that f is a function?
Yep, we know it's a function. So now we just need to show it's a 1-to-1 function.
So just show that f of x equal to f of y implies x equal to y.
Where did you get that great idea?
The definition agrees.
Using its definition directly?
What's
Wonderful.
It's like that's what you're supposed to do in a proof.
So 2, let x, y in z such that f of x is equal to f of y. Maybe x and y are the same thing, maybe x and y are different. We're just grabbing two elements and saying, let's assume that we have two elements such that their right-hand elements are the same. Now we need to show that this implies that x is equal to y.
Pretty simple.
Pretty simple. What do we do then?
When you plug in 3x plus 4 equals 3y plus 4.
Right, f of x, we know what that is. What is f of x?
3x plus 4.
Yeah, then 3x plus 4 is equal to what?
3y plus 4.
3y plus 4? That's what f of y is?
No, it's just that one.
Well, eventually we're going to figure out x equals y.
It's just what?
X.
Is it just F of Y?
Yeah, f of y is just f of y,
Well, what is that?
but it's also 3y plus 4. Don't be confused by the fact that we're using x's and y's. I could have used a's and b's, I could have used anything. Let's look at this function for a second. 3x plus 4. Let's try and break this weirdness you get in your heads from lower school. What is f of 2?
10.
It's 3 2's plus 4. What is f of SpongeBob?
3 squares.
It's 3 SpongeBob's plus 4. What is f of y? It is 3y's plus 4. Anything you plug in here, you plug in there. That's what this is saying. Whatever your x is, put 3x there.
Wow.
Make sense?
Yeah. Makes pennies.
That's enough. Okay, so yeah, f of y is also just 3y plus 4. Then x is equal to y. We won't bother with it from there.
Makes no sense. No, it actually. Change our function to 3x squared. Change all your x's to squared. Can't you follow the same group and come to the same conclusion?
So if I have, okay. Well,
Just
let's see where we go wrong. So I have 3x plus 4 equals 3y plus 4. What do? I subtract 4 from both sides. So I get, or I add negative 4 to both sides, right? We understand from logic, with any operation and any element in our domain, we can always do that operation and that element in our domain and put it on. And we're still good. So I know that I can add negative 4 to both sides. That gives me 3x is equal to 3y. And then I can multiply both sides by 1/3, which gives me x is equal to y.
okay.
Now, Jake was saying, well, what if we had 3x squared is equal to 3y squared? Okay, then I could get 3x squared is equal to y squared, or 3y squared. Then I could get x squared is equal to y squared. Then what?
Get the square root of both sides.
But
You're saying we
but
don't have
then
the
it
square
can
root
be-
function?
What's square root?
What's
It
square?
is-
What's square?
X times x and y times y.
Square root is the number such that it times itself is equal to that.
But there's two numbers.
They're the same number.
What definition are you given for square root that disallows negative y to be the square root? Because negative y squared is not y squared.
Right.
So you can't define the square root in that way to be one and only one number.
Right.
And if it's not one and only one thing, it's not defined. So it's not a definition.
Right, you have to take the positive square roots, which you can't just do.
Right, so that's where we get stuck. And we could prove in this case that it's not. So you'd understand if I go back how it was. So let's prove that something's not one-to-one. So let f be the function given by f of x is equal to x squared. How do I show that this function is not one-to-one?
You simply map it out with a
You
counterexample.
come with one counterexample.
One counterexample. Observe that, pick whatever number you want, 2. So observe that f of 2 is equal to f of negative 2,
But 2 is not.
But- 2 is not equal to negative 2, and we're done. So it's not one-to-one. Pretty easy.
This math proves it.
It's simple in that we're not dealing with complex concepts, but it's hard in the sense that we're dealing with
Functions.
very simple, low-level concepts. There's a weirdness to it where you need it to just be complex enough for it to be nice and intuitive. It's kind of like looking at the world around you. The very small is unintuitive, the very big is unintuitive, but when it's just the right size, it's very intuitive how it works.
So that's what we deal with.
It's what you're familiar with. It's what you deal with on a day-to-day, and it happens that the middle stuff tends to be very useful for day-to-day life. Whereas very low-level sets, we don't deal with those a lot. We're not very comfortable with them.
Right.
And then very complex structures like a space-time, that's also very hard for us to deal with. But somewhere in the middle, when we're just adding natural numbers together, it's nice and easy. So we did that. So let's move on. What are we saying here? On 2. So let f be a function from a to b. Remember, once I tell you f's a function from a to b, what do we know? We know that the domain is a and the image is a subset of b.
Yeah.
Right? So we say that a function is on 2, provided that the image of f is all of b. So it's not just a subset, but it happens to use all of b.
Is on 2?
Yes, on 2.
That's what we're calling it. It's an
Uh-huh.
on 2 function. Okay. Sounds like you're saying like on 2. Snap on 2.
Yep, and that's what we call it, on 2. So that's a pretty simple definition. Any questions with that one? Do we need to see examples?
Saying everything's mapped to every b.
Maybe go over some.
Every a is mapped to one b. Is that what you're saying?
Let's look at this one. Let's go back to f of x is equal to 3x plus 4 on the integers. Is this on 2?
Yes. I think every 1-to-1 is going to be on 2.
Is
No.
every 1-to-1 function going to be on 2?
No.
Let's see if we can come up with an example real quick.
We already did.
So let's make a 1, 2, 3, 4. No, we'll just make it 1, 2, 3. And we'll make b 4, 5, 6, 7. And we'll have the function map 1 to 4, 2 to 5, 3 to 6. So here's a, here's b, here's our map. F is 1 to 1. It's not on 2. Nothing goes to 7.
I was looking at a graph in my head.
You were looking at a function from the real numbers to the real numbers.
Yeah.
So if a function is from the real numbers to the real numbers and it's on 2, and it's 1 to 1, let's come up with one for that real quick. Well, don't make me use the real numbers, but let's just say the integers. How about that?
Sure.
So let's say f is just on the integers, and we'll say f of x is equal to 2x. What's the domain?
All integers.
What's the image? All the evens.
All the evens.
Yep, we never get 3, for example. So there's a function that's 1 to 1, but not on 2.
Doesn't work so well for the real numbers though, right?
Yeah, the real numbers, that's more complex, but we'll stick with simple examples for now. So that's what it means to be on 2. Now, if a function is 1 to 1 and on 2, then we say that the function is a bijection.
And that's most functions that you get in algebra, right?
X equals y.
Sometimes you get functions
Well,
that...
except for like squared and to the power of 4, so like, you know.
X equals y, that function. That's going to be 1 to 1.
Yeah, x equals y, if you sure, f of x equal to x is a better way to say that. Yeah, that's a 1-to-1 function, that's an on 2 function, so it's a bijection. If it's 1 to 1 and on 2, then it's a bijection.
Okay.
And then well, no, we won't get into that. So let's look at an example real quick. So we have A is equal to the set 1, 2, 3, 4, B is equal to the set 2, 4, 6, 8. Then f from A to B given by f of x is equal to 2x is a bijection. Right? Now, before we continue, maybe some high-level discussion. A bijection is, when we're looking at just sets, we'll get to this more, I think, when we do set theory. But a bijection is like our lowest level version of a structure-preserving map. So if I can take a set and create a bijection from that set to another set, what do we use that for? Well, how can I say this simpler? When we're looking at a way that sets might somehow be the same, So remember that we think about ways that we talk about people are the same. We can say, oh, they're all the same height and create an equivalence relation with that. And that's somehow people are the same that way. In geometry, we said with congruence. What's a way that we might say two sets are the same? So I have a set A, B. They're not identical, but I want them to somehow be the same. What's something I might do?
Somehow be the same, is that what you said?
Yeah, what's a set that I can create that's not identical to this, but somehow the same as this?
Couldn't you use something like the same cardinality?
Yeah, maybe do 1, 2. Somehow those sets are the same, right? How are those sets somehow the same? What's the structure that they have in common?
Same size. What?
They have the same size. They have the same number of elements. And so this is actually how we start saying that two sizes of sets are the same. The question we ask is, can we create a bijection from one set to the other set? If we can, then those sets are somehow the same size. You might think that the way that we check two sets are the same size is count everything in one set, count everything in the other set, and that way we determine that they're somehow the same size. But that's actually a harder way to do it. So for example, without looking, I can say, there are exactly as many left eyes in this room as there are right eyes in this room. How did I know that?
So for every left eye, there's a right eye.
Yeah, I knew that I could create a bijection from the set of left eyes to the set of right eyes. And I knew that those counts were the same, even though I never counted how many eyes there were. So, it's one of the most fundamental things that we can talk about is two things are somehow the same size, even if we can't count them. And it's one of the ways that we say that the natural numbers and the integers are the same size. There's the same many natural numbers as there are integers. How do we know? Because I can create a bijection from the natural numbers to the integers. I can map every natural number to one and only one integer.
But not from the integers to the rationals.
Yes, I can. If I can create a bijection from this set to this set, I can create a bijection. Oh, you said to the rationals. Yes, also to the rationals.
Also to the rationals.
Also to the rationals. It's to the rails that you can't do it.
When you
So
start
rails-
dealing with
right.
infinity, it just gets messed up.
Well, then you get to different types of infinities. So the first infinite that we talked about is the countable infinite. The size of the natural numbers is what it is. And then it turns out there's the same many integers as there are natural numbers. There's the same many rationals as there are natural numbers.
Not true.
But there's a different number of reals.
What function do you use to map the integers to the rationals?
Well, that one I'd have to sit and think about for a second. But for the naturals to the integers,
That's an easy one.
that's an easier one that you could easily do.
For every one, you have a negative one. It's twice as big. The integers should be twice as big as the natural numbers.
Integers should be twice as big as the natural numbers. So let's think about it real quick. So let's take a function. And we want it for every natural number to spit out one and only one integer. So what will we do? We'll make it equal to, we'll do 0 if n's equal to 0. Are you good with defining functions this way?
Yeah.
Where you put the cases over here and then whatever else over here. And then we'll do, and let's see, how would I want to do it? I want to do 0 to 0, I'd want to do 1 to 1, I'd want to do 2 to negative 1, I'd want to do 3 to 2, I'd want to do 4 to negative 2. So I'd want to follow a pattern like that. So if it's even, so if it's odd, what's the pattern there? 5 goes to 3, and 6 goes to negative 3. So I see what the negatives are. Divide by 2, so let's wrap the negatives real quick. Negative n over 2, or divided by 2, however you want to say that, if 2 divides n, if n's even. And then n plus 1 over 2 if otherwise. And so that could be our function that maps the natural numbers to all the integers. Every natural number will be paired to one and only one integer, and every integer will be paired from one and only one natural number. And you can take the time to show this as onto and 1 to 1, exactly the way that we've been doing it. Anyways, so that was a side note about bijections. They come up all the time. And in topology, we'll be dealing with a very special type of bijection, our structure preserving that, but I guess we'll get to that when we get to that. Some people also, when they're talking about bijections relative to sets, if you can create a bijection between two sets, they say two sets are isomorphic. Saying two sets are isomorphic, that's the terminology we use in set theory, just like we say two triangles are congruent when we're in geometry.
So what is the definition of isomorphic?
Set A is isomorphic to set B if and only if there exists a bijection from A to B.
That's literally it.
Uh-huh.
Are there other definitions of the context of that word? I feel like I've heard that.
Yeah, so there's also an isomorphism in abstract algebra, not algebra like we're used to. And we'll come to it. The one that we'll see in topology is called the homeomorphism. We'll see what these things are like. So we talked about a bijection. Operation. So we dealt a lot with operations. A common operation that you use is plus, for example. Plus is an operation. What does the plus do? You give it two numbers, and it spits out a number. That's what the plus operation does. Similarly with the times operation. You give it two numbers, it spits out a number. So an operation is something that takes two elements from your set and spits out an element. So let's look at it. Let A be a set. Then a function f from A cross A to A is called a binary operation on A. Make sense? Mm-hmm. F is a function whose domain is all ordered pairs we can get from A, and whose image is a subset of A.
Does it have to be just A, or can we do a function from A cross B to C? Is that a thing?
I can do a function from A cross A to something else, and then it would just be a binary operation. Here, the way that they're using binary operation, it's the same thing as a closed binary operation, a closed operation.
Okay.
Here we're not going to worry about closed versus not closed. But you did have that in discrete math, if we did algebra. I can't remember which classes I did what with.
With your first class, you did graph theory.
Oh,
And then in algebra, we only got like 1 or 2 sections in before it ended.
but we will have come across an operation right out the door
Oh, yeah.
for groups.
Yeah.
Because a group
It was like
is dealing with an operation. That's what a group is set with an operation. All right, so let's look at an example. We could look at the example. A is a set 0, 1, 2, and I create some operation F right here. It takes 0, 0, spits out 0, takes 0, 1, spits out 1, takes 0, 2, spits out 2, takes 1, 0, spits out 1, takes 1, 1, spits out 2, takes 1, 2, spits out 0, 2, 0, spits out 2, 2, 1, spits out 3. Oops. That's supposed to be a 0. And it takes 2, 2, and spits out 1. There's an operation. Good? What was I doing for this operation? I was just adding the numbers together, and if they went out the set, I came back around.
Isn't that
Modular arithmetic,
Yeah.
yes. So when I did 2 plus 2, so I got 0, 1, 2, add 2 more, that gets me to 1, is what I was doing. So that's the operation I happen to choose to write out, but any set that satisfies, or any function that satisfies this requirement is an operation on A. Maybe it has no logical order to it, maybe you can't figure out any pattern it's using, maybe it feels completely random, doesn't matter. Here's an operation that we all know and love. The plus operation takes 2 real numbers, spits out a real number. What's an element inside of here?
well, any real number you want?
1, 1. And what's paired with 1, 1?
2.
2. What's paired with 0.5 and 0.3?
0.8.
Comma 0.8. And obviously there's infinitely many things in there. But that's what we mean by the plus operation. We mean this relation, or this function. That's what an operation is. Any questions on that? Seems simple, seems straightforward. That's functions. We'll get lots and lots of functions, continue with math. Basically off topology, we're just talking about sets and functions on sets. Now we'll move on to an operation we can perform on functions called composition.
What is all this writing over here?
Calculus.
That's literally what it looked like. I was like,
Yeah, you remember some of that?
yeah.
Sure hope so.
I remember that definition.
The definition of absolute value?
No.
That's the definition? Oh, the definition of,
N over K, whatever it is.
oh, and choose K?
Yeah.
We'll finish the rest if we need it. Okay, so composition. Let's see. So this is the definition. Let A, B, C be sets, and let F be from A to B, and G be a function from B to C. Then G composed with F is a function from A to C defined by, okay. Then, let's see, we're gonna do G composed with F, that's the way we write it, is a function from A to T to C defined by G composed with F of A is equal to G of F of A. For all A in the set, for all A in big A. So let's draw a picture of this and then go over it again. It seems very dense, but it's actually a pretty simple operation. So we have three sets, A, B, and C. 1, 2, 3. We'll make this 2, 4, 6. And then we'll make this 6, 12, 18, something simple. So we'll say that F is this function. It maps 1 to 2, 2 to 4, and 3 to 6. And G is this function. It maps 2 to 6, 4 to 12, and 6 to 18. Then G composed with F. G composed with F. Another way that we sometimes read that is G after F. Takes 1 straight to 6, 2 straight to 12, and 3 straight to 18. And we skip over the middle.
You should have mapped it a little more funky so that you made your message.
Well, I think the message is fine, but let's bring this other arrow around. Should have done that way. There we go. So it's combining two functions into one function. So that's pictorially what it looks like. Let's write these out to help hammer the point home. So F was equal to, what's in F? 1, 2, 2, 4, 3, 6. What's in G? 2, 6, 4, 12, 6, 18. Then, let's see, G composed with F. What's in that?
1, 6, 2, 12.
And notice that G composed with F of 1 is equal to what? 6. It's paired with 6. Well, also look at g of f of 1. What's f of 1 equal to?
2.
F of 1 is 2. So now we have g of 2. What's g of 2 equal to?
6.
G, what's paired with 2 and g? 6. So this and this give the exact same thing. Make sense?
Yeah.
So that's function composition. Is a way of combining functions together. Let's do it with just some algebra ones that you probably would have done all the time. So let's say that I have a function f of x is equal to 3 plus 2x, and let's say that g of x is equal to x squared. With me? We're assuming that these are functions from the real numbers to the real numbers, like you're used to dealing with. Okay? So now, what is g of f of x? G of f of x is
3 plus 2x all squared.
g of f of x. Let's just use this directly for a second to help us think about it. But what is f of x?
3 plus
3x plus 2. So this is equal to g of 3x plus 2.
It's 3 plus 2x.
Oh, thank you. 3 plus 2x. And what is g of 3 plus 2x?
3 plus 2x squared.
3 plus 2x squared. Right?
I'm missing an x then.
9 plus 12x plus 4x.
3 plus 2x squared. Am I missing an x?
Wouldn't you have to times the number?
I'm plugging this in to this function. Gives me this squared.
Oh,
Right? So now let's compare that with, let's do f composed with g. What do you think? Same thing or different?
Different.
Different?
100%.
Alright, let's look at f composed with g of x. What's that going to be?
It's going to be
3 plus 2x
f
squared.
on the outside and then gx.
Yeah, we could do f of g of x first if we want. And then that's going to equal f of x squared. And that's just going to equal 3 plus 2x squared. Right?
Yes, sir.
Plug in whatever we put in here in for x. Make sense? So that's function composition. And notice we can pick any number we want and run it through, and we get the same thing as just putting it in there. So let's do it. So let's do this one first. This one was f after g. So let's plug something into g, then plug it into f, see what we get. And then we'll just plug it into this and see what we get. So we're doing g first. Pick a number. 4. What's 4 squared? What's 16 times 2? Plus 3? 35. So we got 35. Now let's just plug it in directly. 4 squared
16.
times 2? 32. Plus 3? Ah, we got the same thing. Now let's try it the other way. So this time we'll do plug into here, then here, and make sure that's the same as this. Pick a number.
2.
2. 2 times 2 is 4, plus 3 is 7, squared is 49. Now let's plug into here. 3 plus 4 squared is 49. Ah, she laughs because it became obvious that we were going to get the same thing. Right?
Wait.
Oh, you screwed up in your head?
That's perfect, actually.
So, the mapping works. That's how function composition works. So you've seen it with discrete sets like this. You've seen it with algebraic equations like this. That's how function composition works. You're just putting two functions together into one function. Now, notice if I have, if I know that f is a function from a to b, and I know that g is a function from b to c, then if we have g composed with f, well, here's how it says. What is the domain then of g composed with f?
A.
A.
It's just A, right? Because we run everything through F, and then whatever F spits out, we run through G. So it's just whatever came from F, so what's the domain of F? It's A. So the domain of G composed with F is the same thing as the domain of just F is equal to A. Notice that when we had this for G and this for F, the domain of G, 1, 2, 3, the domain of G composed with F, 1, 2, 3, is the same thing as the domain of F, 1, 2, 3. And the image of G composed with F, 6, 12, 18, it's not always going to be the image, but it turns out it's going to be a subset of the image. We'll come up with an example where it's not equal. But the image of this is always going to be a subset of the image of this. Make sense? Covered that. And similarly, what if we also had h as a function from C to D, and we did some big composition? What is the domain now of h composed with G composed with F? Still just A, right? It's the domain of whatever the first function is, the one that you run first. That's where all the elements come from. So, we don't need to go into trig functions and arc trig functions. I don't know, I don't want to do it unless you guys are all very familiar with trig. How do you guys understand what I mean by arc sign?
Yeah.
Well, I mean,
What's the arc sign?
I have an idea of what it means, but I couldn't, I'm not.
Okay.
You just
He's just giving it as an example, so no point doing it if it's just going to cause issues. Okay, one more point to note. I don't know if this is the last point he's going to note. Looks like it. Is if f is a function from, we'll look at a function from A to itself. So I'll say now that f is a function from A to itself. The question is, what is f inverse composed with f going to be?
What is it going to be?
Yeah. What's it going to ultimately do?
go back to F inverse.
So let's draw out a set real quick and see this in action. So let's pick some set A. Give me some elements.
It's gonna be equal to.
5,
5,
2,
2,
6,
6,
8.
8. Alright, so we got 5, 2, 6, 8 up there. Let's make f the function what?
3.
It can't. It has to be from A to A. So you can only use elements in A.
Oh.
5, 2, 6, 8.
5, 2, 6, 8,
2, 6.
2, 6.
8.
What are we left with?
8.
6, 5.
8 goes to what?
8, 5.
8 goes to 5. Right? So there's a function. It has to use, remember, for it to be a function from A to A, it has to have every element in A as a domain. So it had to use 2, it did. It had to use 5, it did. It had to use 6, it did. It had to use 8, it did.
Basically,
And we want the inverse to also be a function, so I needed to make sure it was a one-to-one function.
is that going to be A cross A?
This is a subset of A cross
I'm
A.
saying is your answer there. F inverse compose F. Is that A cross A?
So let's look at what it is, but first off, let's do F inverse.
I mean, it's going to be 5, 5, 2, 2, 6, 6, 8, 8.
Yeah,
What's the way of saying that?
it's going to pair every element with itself.
Yeah.
Nope, it's not going to turn out to be the same function.
No, it's not. It's going to be, this of x is going to equal what we call the identity on A.
There we go. That's what it is.
It's going to map every element in A to itself.
Of course.
So F inverse is going to be 2, 5, 8, 6, 6, 2, 5, 8, like that. So we do F first. Let's look at what happens when we plug in 5 to this. So 5 goes to 2, then 2 goes to 5, so 5 went to 5. Make sense? Similarly with 6, 6 goes to 8, goes back to 6, so 6 goes to 6, etc.
How do we do proof for that?
Say that again.
How do we do a proof for that?
How do we do a proof that that's equal to the identity on A? So when you're proving that two functions are equal, you need to show that they have the same domain, and you need to show that they map every element in the domain the same way. So if I want to prove that this is equal to the identity on A, first off I'd say, okay, what's the domain of F composed F inverse?
Well,
It's just equal to A, which is definitely equal to the domain of the identity on A.
Right.
Because the identity on A maps everything in A to itself. So they have the same domain. Check. Now we need to check that this, when we put in A, gives me identity when we put in A. So then we say, let A in A, then F inverse composed with F of A is going to equal F inverse of F of A. We need to specify whatever that thing is going to be.
Call it Z.
So let A in A, comma, and let, or maybe, how's a simpler way to do this?
You don't have to. You don't have to define your function, do you?
Let A in A, comma, and let B in A such that AB is in F, something like that.
Right.
Let A in A and let B be the right-hand element that gets paired with A and F. And I would also note that implies that BA is in F inverse, so I'm going to need to use that fact. So then F inverse of F of A is equal to F inverse of A is equal to A is equal to
F inverse of B.
the identity on A. The identity of A on A. So they both map A the exact same way.
You should.
It
That
should
should
be
be a
F
B.
inverse of
Oh,
B.
sorry, yes. F inverse of B. And that they show that the two functions are equal. But,
It's coming back. All the pain.
yeah, what class do you take during discrete math? Maybe you should give it up and just come sit in on discrete math.
Oh, I would so do that.
Alright, let's see one more example of this, except for using algebraic equations like you're used to. So we'll just keep it simple. Let's let f of x equal 3x plus 2. What's going to be the inverse of x, first of all? Have you guys ever learned how to calculate an inverse function?
Yes. You switch them when you solve for x.
Right, so one way, when you say switch them, what you're saying is
Switch
make this
x.
equal y equals 3x plus 2. Then switch your x's and y's. X is equal to 3y plus 2. Then solve for y,
Right.
right?
Yep.
So then,
2 divide 3.
Y is equal to x minus 2 over 3. Or in other words, f inverse of x is equal to x minus 2 over 3. That's a perfectly valid way to do it.
Plug it in, and I bet you'll just get.
Another way to do it is to just keep undoing this expression until you're left with x. And, well, I won't say it that way.
Well, now watch, if
I
you
never
plug-
like doing that. Never makes much sense. It's just flipping them.
If you
Alright.
compose, now watch, when you compose.
Yeah, now let's compose them. So pick a number.
2,
2. 3 times 2 is?
6.
6.
6 plus 2 is?
8.
8 minus 2 is?
6.
Divided by 3 is?
2.
So it maps 2 to 2 when you do them both.
Well, you know.
And we
when
could
you
also
compose
do
them
the
together-
inverse of it.
Well, when you compose them together, look what happens when you compose them together.
That's what we did. Oh, you just want to see it directly. So you're saying let's just look at f of f inverse of x, right?
Yeah.
So let's just write that out.
Yeah, and repeat them then.
So then we're going to have, I'm going to rewrite over here to give me space. So we have f of, what was f inverse of x? It was x minus 2 over 3, right?
Yep.
And then that's going to be equal to, plug that in for x, we get 3 x minus 2 over 3's plus 2, which is equal to, 3 goes out with 3, x minus 2 plus 2 is equal to x. F inverse of this. Oh, that's f of f inverse. So that is what f of f inverse of x is equal to. Just x. Which is the point we were making, right? Church lambda notation, we won't go over that. You guys won't care about that unless you're going into computer science, and that settles it. So that's the end of functions. Any questions?